Hello, welcome again to Living Physical Geography, Geography 201, and today we are in Chapter 2, The Seasons and the Sun. So we talked about the atmosphere, let's talk about the seasons. Now, the seasons are integral to human society and culture. You think about human society, right, and we have Christmas in the winter, we have Easter in the spring. Many holidays, festivals, religious events are tied to the seasons. I mean, Easter happens for a certain reason every year. It's actually tied to the lunar cycle that happens in spring. Christmas occurs almost always around what we call the December solstice, right? So we have that. But there are two different types of seasons. There's meteorological season, when it's winter and it's snowy, when it's summer and it's warm, if it's dry or if it's wet. That's meteorology, changes in temperature. There's also astronomical seasons, and that's what we're going to talk about. And this is based on where the sun is, where we are in relation to the sun. So those are our four seasons. So the first thing is we orbit the sun on what's called the plane of the ecliptic, right? So this is basically if you do an imaginary flat table, the Earth kind of orbits on top of it around the sun. That's the plane of the ecliptic. Now we orbit not in a circle, but in an oval. And so the oval is actually closest to the sun in January and farthest from the sun in July. But that is not why we have summer and winter, because that would actually make no sense when we're further from the sun in summer. We'll talk about that. That distance between the Earth and the Sun is called the astronomical unit. It's the average distance because it varies. It's on average 149. The seasons are caused by the tilt of our axis. So let me show you what that means. If you drew a line right here between the North and South Pole, right, it isn't perfectly straight to the orbit of the ecliptic. We rotate tilted. So we rotate on a tilt, which is 23.5 degrees. That's our tilt. And what that does, okay, a couple things. The north, if you were at the North Pole looking straight up, you actually wouldn't go, you would see the North Star. But here's what happens. So we tilt. This tilt stays the same as it goes around the sun. It stays 23 degrees as we go around the sun. So right here, at this time of the year, the top of the Earth, the northern half, is tilted away from the sun, and the southern half is tilted towards the sun, which means that this gets more sunlight. The opposite time of the year, the northern half is tilted towards the sun, the southern half away from the sun. So the northern half gets more sunlight. And here in between, the tilt is such that every part of the Earth gets the same amount of sun. So this is, for us, summer. Longer days, there's more sunlight, more heat. This is winter. Shorter days, less heat. Spring and fall. Let's talk more about that. We explore this idea of the subsolar point. Okay? So because of the tilt, right, I'm going to come back to these. It's better, I think, to start with the picture. Here's the Earth, right? And on this day, this day would actually probably be in March or September, the sun is right here. So the sunlight hits the Earth right here. This is the angle between where the sunlight comes in, and the further north you go from the equator, right, there's more of an angle. That's called the solar altitude. Where the solar altitude is the highest, 90 degrees, the sun is directly overhead, this is the subsolar point. Okay? Let me show you another picture. The subsolar point. This is where, if you were at noon, you would have no shadow. Up here, you'd have a little bit shadow right here. This is the part of the Earth that is illuminated by the sunlight, right, as it rotates. That's called the circle of illumination, the half of the Earth that is always lit up. And the subsolar point is always in the middle of that. So let's go back to those definitions. That's the circle of illumination. That's the half of the globe that's illuminated by the sunlight. The subsolar point is always in the middle, right? And the subsolar point determines altitude, how high the sun is, or the intensity. Now, this is the Earth not tilted. So this would happen in the spring, but we know the Earth tilts. So if the Earth is tilted, the subsolar point is going to migrate. If there was no tilt, the subsolar point would always be on the equator, and each half of the Earth would always get the same amount of solar energy. There would be no seasons, because there would be no change in temperature. It would always be what it is. But the tilt changes that. By the way, you could say conversely, what if the Earth was tilted on this 90 degrees and the North Pole always pointed towards the sun? Like if we were kind of rolling on our side? Well, then we'd always have one side of the Earth would be in brightness, and one side of the Earth would always be in darkness. Now, what happens is, and I'll come back to these, when the Earth moves around, we have these patterns of solstices. The subsolar points move. So, when the northern half of the Earth is tilted furthest away from the sun, the subsolar point is the farthest south it will be, which is 23.5 degrees. So, on a line around the Earth, 23.5 degrees south, a line of latitude, that is where the subsolar point is, and that is called the Tropic of Capricorn. Conversely, 6 months later, in June 21st, the northern half of the planet is tilted as close to the sun as it will be. Now the subsolar point is about 23.5 degrees north on the Tropic of Cancer. So the subsolar point migrates north and south over the course of the year. Go back to those images. So the Earth right here, if you can imagine, right in the picture, it's going to go like this and this relative to the sun. And so the subsolar point is going to migrate north, south, north, south. And it stays between those tropics. So the solstice, the December solstice, is the point in which the subsolar point is the furthest south. It is the day that we have the shortest day in the northern hemisphere. So it's in December, and the longest night. It's actually the exact opposite. In the southern hemisphere, in South Africa and South America, that is their summer, Australia. They have the longest day and the shortest night. We have the March equinox. This is when the subsolar point is now in the equator. So every part of the Earth has an equal amount of day or night. The June solstice or the summer solstice, the longest day in the northern hemisphere and the shortest night. And then the fall equinox. So you can see right here. So on the equinox, every day on the equinox, which is one day of the year, or twice a year, everywhere in the Earth, the day is 12 hours long. And then the days gradually get longer or shorter as they move towards the solstice, back and forth. So let's put that all together. I know it was a lot of stuff to kind of talk about. Here is the equator, the circle of illumination. So on the equinox, the subsolar point is right here. Every part of the Earth gets 12 hours of sunlight. But the December solstice, the tilt has changed. And now the subsolar point is right here, which is 23.5 degrees south. As you go north, you get less sunlight because some of it's tilted away. So shorter, shorter, shorter. And when you get to be at 66 degrees north, there's actually no day whatsoever because the tilt is such that whole part is tilted away. So this part rotates like this outside of the sun. So on the December solstice, the sun at the North Pole does not rise. It's 24 hours of night. As you go further south, the South Pole, anything below 66 degrees south, the sun never sets that day. The June solstice is exactly the opposite. So now as you go north, you have a longer day, and then as you go south, a shorter day. So it's kind of interesting. In our summer, high areas like in Alaska, Canada, Norway, their days can be as long as it gets closer and closer to the equinox, 10, 12, 14, 16, 20 hours long. And then finally, on the day of the equinox, the sun doesn't set. Or if it does set, it sets for like 1 hour. It's almost like twilight. Okay? and then gradually the day gets shorter and shorter until exactly in winter, the same thing happens. So up in Canada, Alaska, when you get to winter, the sun may rise for only 1 or 2 hours, and at a certain point, it barely rises at all. We're going to pause right here and let your mind wrap around that one for a little bit. Feel free to go back and look at the textbook a little bit on that one. Basically, my big takeaway is this. We know that in the summer, in the northern half of the planet, it is summer. The days are longer, more energy, more heat. And in the winter, they're shorter.